All right, just wanted to remind everybody about the involvement fair next week, or no, sorry, tomorrow, September 11th from 4 to 6 p.m. It is indeed in the Shore Center on the second floor. And School of Computing specific RSOs and organizations will be there. UNL Coding Club, Initialize, CSAB, and a couple, and the UNL Game Dev Club, among others, will be there. So I'd highly recommend that you go to that if you haven't gotten a chance to go to one of the other university-wide involvement fairs. So to continue where we left off last time, we were talking about loops. And we initially looked at for loops. For loops have all three of those conditions: the initialization condition, where you start the loop; the continuation condition, how many do you keep running the loop; and the increment condition, all in the same line. A while loop is different in that it's on different lines, and it also gives you a little bit finer control over it. That increment right there, it can be done anywhere inside the loop, right? So you could be doing it at the beginning or at the middle or the end or something like that, but it changes the behavior of the loop, right? Then we talked about which loop should you choose. And in general, what you want is loops that you use for loops when you know up front how many iterations you're going to execute. If you know that you want to count up from 1 to 10, right, then you use a for loop because you know that there are going to be 10 iterations for that. A while loop is used when you don't know up front how many iterations you're going to run for, because it's some other condition that the loop changes each and every single time. The example that we did here was counting the number of digits in a number. We don't know how many digits are in that number, because if we did, then we'd have the answer and we'd be done and we wouldn't need to write a program. So instead what we do is we have a while loop. While that number is not 0, divide it by 10 and increment a counter on the number of digits, right? And that worked for everything except for, of course, if it was 0, we did that as an exceptional case up here. A while loop, we could do this with a for loop if we really wanted to, and it would look completely different, but it would look really, really unnatural, because you would say, for this condition, and then, how do I know that condition that I've reached 0 or not, right? So, continuing there, there's some common pitfalls that you should be aware of. So, for example, consider the following code. Right? We've got int I is equal to 1, I is less than or equal to 10, and then inside we do I++. Does anybody see immediately what's wrong with this code? Yeah, I heard it. There's a semicolon, an extraneous extra semicolon there somewhere. So let's come over here and see what the output of this program would be, of this code snippet right here. I'm going to go ahead and, there we go. And there, now everything's aligned. GCC demo.c, right? There we go. No warnings. What should I have done, by the way? And we'll do in a second here. That wall flag will actually point out to us what's wrong. But when I run this, what happens? Nothing happens, but it's stuck, right? It's not printing anything. Why is it not printing anything? Well, understand what this is doing. While I is strictly less than or equal to 10, do what? Do nothing, right? And because we're not doing anything, well, we're not changing I, we're not doing anything, it's just sitting there spinning. So let me go ahead and kill it. Remind me, how do I kill a program? Control-C, right? Or Command-C, or whatever it is on Windows, right? Over here on my Mac, it's going to be Control-C, right? All right, so let me go ahead and undo. And let's go ahead and recompile this as we should have with that wall flag. Warnings, all of them. Give me all those warnings. And it'll tell you, warning, this while clause does not guard, right? This statement, but the latter is misleadingly indented as if we're part of the while, right? In other words, I see an opening curly bracket right here, but there's a semicolon here, and the while loop has already ended, right? So are you sure you meant to do this? Okay. So once again, it will help if you use that wall flag all the time. Right? Again, the problem here is that the semicolon is misplaced. This semicolon right here should not be there. It makes the loop body empty, and we're caught in an infinite loop. Reminder, Control-C kills it, and reminder, the wall flag will catch stuff like this. So be careful. Actually, just use the wall flag, right? Here's another example. Right? Here's a piece of code. What's wrong with this? So I start out, I is 0. I is strictly less than 10. then I print I. What? Yeah, I didn't increment, right? There's no increment, and so what will happen here? An infinite loop. The result, infinite loop. No progress is made. Always prints 0. Right? So that one's pretty straightforward. What about this one? What's wrong with that code? No curly brackets, right? So let's come over here and see what the consequences of that is. Right? And, oops, I don't want that. Let me go ahead and grab it like this, as is, and put it there. All right, I will, there, indent. Come on, indent. There we go. All right, once again, I'm going to compile this, but I'm going to forget the wall flag. And GCC is perfectly happy with this. What do you think is going to happen without those curly brackets? I is going to be set to 0. Is I strictly less than 10? Yes. So do what? Without those brackets, it says only do the next thing and only the next thing. In other words, this I, even though it's indented, is not part of the code block. It's as if it were over here instead, right? So print 0, print 0, print 0, right? And indeed, I get into an infinite loop here. I never actually increment I++. So it is always best practice to include those curly brackets even if you don't need them. Right? Let me go ahead and roll that back and show you that also the best practice is to use the wall flag. Wall would have warned me about this. Right? Whoa, wait. This while clause does not guard. Note this statement, but the latter is misleadingly indented. This I++ is indented as if it were part of the while block. Right? So make sure that you've got curly brackets at all points and make sure that you're using the wall flag to detect things like this. This is just bad style, right? Bad style, however, leads to not syntax errors, but logic errors. In this case, the loop is only bound to the next executable statement, and that's it. The increment never actually happens, thus resulting in an infinite loop. Right? No matter what, always use the best practice and always have your curly brackets there. Okay? Restoring the curly brackets as in the ones up here, that'll solve the problem there. And this is not a common error, but let me go ahead and give you. Well, first of all, let me give you. It's a funny bug, right? And as we go along and get more and more into the 21st century, I find more and more people who never even heard of the Zune before, right? So who has heard of the Zune, Microsoft product? It was, all right, good. Well, a lot of you, all right. So the Zune was an iPod competitor that Microsoft put out. It was less expensive. It had a radio, and so it had that going for it. But on December 31st, 2008, every Zune froze for 24 hours. 24 hours later, every Zune came back up. What was the problem? First of all, tell me what is it about that date now that you've done your lab yesterday? 2008. What was special about 2008? It was a leap year, right? What about December 31st? That was the last day of a leap year, right? So somewhere hidden in it was not Microsoft code. It was some other subsystem code. They had this code, right? So while days is strictly greater than 365. In other words, it is December 31st, 2008. It is day 366. This while loop will now execute because 366 is strictly greater than 365. Is it a leap year? 2008. You wrote that code, and that's correct, right? It is a leap year, so this evaluates to true. So we now go into this block right here. If days is strictly greater than 366, is it? No. It is equal to 366. And so consequently, this code that should have executed that wrapped us around back to day 1, right, and then incremented the year to 2009, this never happened. Right? So what happens? This is an else statement, and since this is true, the else statement does not execute, so we come back right up to the top, nothing changed. It is still day 366. 24 hours later, after it's doing this while loop the entire time, 24 hours later, it is now day 367. Right? This is true. It's still a leap year, but now 367, this ends up being true. We subtract 366 from this. Now it's day 1, January 1st, 2009. We increment, well, year, now it's 2009, right? So, what's the problem here? I mean, obviously, you change this to greater than or equal to, and you solve the problem. So that's the bug. But really, what's the real problem here? Testing, right? Did anybody think to test it for those corner cases, right? We've got code that checks to see if it's a leap year. Do we have those 6 test cases that you wrote for your lab, right? Do we have maybe at least 1,000 test cases automated that will test that for the next 100 years or something, all the leap year calculations are correct? Did anybody think to test it on, well, what happens on that last day? Because there's this code here that's supposed to execute on the last day of a leap year. Should we test what happens on the last day of a leap year, right? So the real problem here was not the actual bug. There's always going to be bugs. You're always going to write buggy code. But the real problem here is lack of testing, right? Testing and testing those corner cases, giving your code a nice, healthy workout, that's that's where the real work is, right? You need to test all possible edge cases or corner cases and see what happens. What happens when it's at 0? What happens on that last day of a leap year? What happens on the first day of a leap year, et cetera, right? So, nice little bug here. And by the way, it didn't really matter because it just the thousands of people that owned a Zune, such as myself, were inconvenienced for a day. But imagine if this kind of bug occurred in a mission critical system, something that was a control system for air traffic controlling, right? Medical devices. And this has happened before. There have been bugs that have killed people because they got too much radiation dosage out of a system, or that have cost hundreds of millions of dollars. Another famous one was we lost 2 Mars rovers in the 90s. One of them was because one subsystem was using metric, like they all should have, and then another subsystem was using imperial, like feet per second or something. And so instead of thinking that it was gently landing on Mars, it was careening like full force and crashed and blew up. Right? No people in it, but that's cost the entire mission was scrapped. It cost hundreds of millions of dollars and thousands and thousands of man hours down the drain because somebody couldn't convert from metric over to imperial. The real problem there, of course, was using imperial at all, right? You don't do that in any real system in any scientific endeavor, right? All right, so we're not going to have such terrible bugs in this class, but testing will be up front, right? You'll be doing testing informally, then you'll eventually do it a little bit more formally, and then finally you'll do it very formally when we introduce CMACA and a formal unit testing system. Right? All right, some other things that you should be aware about with respect to loops. You can have nested loops. A loop within a loop is called a nested loop. There we go. And there is an outer loop and an inner loop. Right? All right, so let's come over here and take a look at an example. And I'm just going to keep it simple by using for loops instead of while loops. Okay? I'll go ahead and set n here to 10. And what I'll do is I'll set a for loop to run from I equals 0, I is less than n, I plus plus. Remember, that's your idiomatic for loop, right? That's the loop that is going to be the most common loop that you're going to write for the rest of your life, right? At least for this class. All right, now I want within this loop, that's the outer loop, I want another loop inside of this. For int, can I use I? No, why? Where have I used I already? In the outer for loop, right? I might be able to use I, but then it's going to confuse on which one are you talking about, right? In fact, let's go ahead and try it. I is equal to 0. Hopefully the compiler doesn't even let me do this. If so, then bad compiler, shame. Right. Printf, hello. Just for now, I'll say hello. Let's see if it even compiles. GCC demo.c. Oh, it does. Bad compiler. At least will you warn me about it? No, you will not. Right? Bad. All right, so yes, you can do that, but I have no idea what you're going to get. Let's try it. Hello, hello, hello. Looks like it might work. I have no idea what it's doing though. So anyway, in any case, that's a bad idea. What variable name should we use instead? J. Why J? Comes after I, right? J is equal to 0. J is less than n. J plus plus. Right? Remember that I has somewhat of a meaning. It stands for iterator, or it stands for index. J, it's J because it comes after I. You'll find out that that's a very common theme in computer science. We're learning C right now, but you might have heard of C++. Why'd they call it C++?
Because it's C that's been improved upon.
Yep, because it's just the next one, I++, right? Or for those music fans out there that actually play music, I don't play any music. C# is another programming language. It's Microsoft Java. What does the sharp mean here in C? You have the note C. It's is one half note up or what?
Yes.
Half step? Yep. Okay, half step up. There you go. Right? And by the way, why do we call it C? There was an A and a B. Right? There was a programming language called B, and then they just said, okay, well, what's next? C. Right? Not that creative. Right? But in any case, we'll go ahead and we'll go with J because that's next. Let me go ahead and print out I and J is equal to, and the line, %D, and the line, I and J. And let's go ahead and compile this, and let me clear this out so that I don't have anything there. And let's jump all the way to the top here. You'll see that when I is 0, that entire inner for loop there is going to execute all the way from 0 up to 9. Only then does control go back to the outer for loop, and then I gets incremented to 1. The inner for loop once again repeats 10 times from 0 up to 9. So we do that for I running from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 until they're both 9s. Right? How many total iterations did we run, by the way? 100. Why? Int count is equal to 0. Let's go ahead and verify that first experimentally. Count plus plus. Printf count is equal to %D and the line count. GCC. Right. Run this. 100 was right. Why? The outer for loop runs 10 times. The inner for loop runs 10 times each for the outer for loop. So 10 times 10. That's a fundamental relationship in a lot of algorithms. Is it a good idea? Let me go with 100 here. Now how many times is it going to run? 100 times 100 is 10,000. Let's find out. Indeed, it's 10,000. Right? And it was pretty quick. If I go up to 1,000 though, 1,000 thousands is what? A million. So programs are what's called I/O bound, right? And we will get there eventually here. But input and output are the most expensive things that you can do in a computer. If all you wanted to do was some simple operation here where you didn't actually have to print anything out, right? That took a while. That took like 30 seconds or something. But if I took out the if I took out the print statement there, it would go by in an instant, right? Because the most expensive thing that you're doing is outputting stuff. Right? Computer is way faster than printing all that stuff out. Right? As long as you don't ask it to do the most difficult things like I/O, then it can go by pretty fast. However, there is a limit. I add 3 zeros there, so 1 million. So 1 million 1 millions, what do we call them? Trillions, right? So is this going to execute in an instant? No way, right? Even a simple thing like counting 1, 2, 3, 4, all the way up to 1 trillion, that's going to take a computer a long time. And by the way, it won't work because, of course, we'll have overflow at some point. 2.147 billion is the largest that it can represent. So it'll go back out down to zero. Then it'll go all the way back to zero, or it'll go negative, and then it'll go back all the way to zero. Then it'll go up all the way to 2.147 billion. It'll go around that circle several thousand times, right? I'm not going to sit here and wait for it, right? So the takeaway here is, let me go ahead and kick it back down to 10 when I go ahead and copy it to the code, to the notes here. But the takeaway here is that nested for loops, or nested loops in general, can be extremely inefficient. This can be extremely inefficient, right? If you have a nested loop, think, is it really necessary? Many times, yes, right? Sometimes, many times, yes, that's what you have to do. But otherwise, rethink what you are doing, right? Small inputs may be okay, but large inputs can take a long time, right? That's where you get inefficiencies like this, right? And later on, when we start covering algorithms and algorithm analysis, or we introduce those notions, we'll look at this formally. This is an n squared algorithm right now, because the outer for loop, it runs for n times, the inner for loop runs for n times times n, like 10 times 10 is 100, 100 times 100 is 10,000, a million times a million is 1 trillion. The commonality there is n times n squared. Right? And when you double n squared, it doubles by a factor of 4. When you go up by a magnitude that is 10 times bigger, it goes up by a factor of 100 because of that square factor. Right? So really rethink what you're doing there. And by the way, you can mix, you can have a while loop inside of a for loop inside of a while loop, et cetera, et cetera. Right? The only other miscellaneous thing that I'd mention is do while loops. Right? C supports do while loops, but you can safely ignore them. I think Zybooks might have a chapter on, or not a chapter, but like a section on this. The only difference is that a do while loop is it's executed unconditionally, at least on the first time, and then the continuation condition is checked at the end of the loop instead of at the beginning of a loop. Right? The continuation condition. Should I go one more time? A while loop and a for loop check that at the top. A do while loop checks it at the bottom. Right? And so if you're interested, go ahead and read more about it, either in the Zybooks, if it has any, or in some other resource. What I wanted to do for the remainder of our time is do some exercises, as many as we can here. I've got a whole list of exercises. I've got a whole book of exercises, right? All right, the first exercise is going to be the classic, what's called FizzBuzz, okay? So what is FizzBuzz? Well, FizzBuzz predates, I believe, this article from 2007. I think so FizzBuzz is probably like 20 years old by now, 25 years old. But it's all started, it became popular with this article posted by Jeff Atwood. Does anybody know who Jeff Atwood is? He's one of the co-founders of Stack Overflow. Anytime you post a coding question on Google, what's the top hit? It's at least it used to be Stack Overflow, but it's kind of Stack Overflow is on its last leg right now. Anyway, so a whole bunch of people have this common complaint that when they're trying to hire programmers, when they're trying to hire developers, they can't do the simplest of programs. When you eventually go out and interview for a job, a lot of times you'll be given a coding test. Sometimes there'll be really simple stuff. Sometimes it'll be like when I interviewed at Google 15, 20 years ago or so, and it was 8-hour day of 8 different people asking me these programming contest level questions. And I didn't have a computer or anything. I had to whiteboard everything. Anyway, it was terrible. I hated it. But FizzBuzz is like one of those trivial ones that everybody that's gone through 3 or 4 weeks of programming should be able to do. But all these hiring managers, all these HR goons are complaining that either they get a candidate that can do it, but it takes them an hour to figure it out, or that 199 out of 200 applicants can't write code at all, right? They couldn't do a simple FizzBuzz program. So what the hell is a FizzBuzz program? A FizzBuzz program, where is it? 100. There. So write a program that prints the numbers 1 to 100, but for multiples of 3, it prints fizz instead of the number. And for multiples of 5, it prints buzz instead of the number. For multiples that are both, for numbers that are multiples of both 3 and 5, so like 15, 30, right, etc., print fizzbuzz instead. Okay. Many good programmers should be able to write out on a paper program which does this in a couple of minutes. Want to know something scary? The majority of comp sci graduates can't, and I'm sure that this has not gotten any better. Right? In fact, it's probably gotten worse, right, over the years, over the last couple of years with ChatGPT. Right? The majority of comp sci majors can't. We've seen self-proclaimed senior programmers take more than 10 to 15 minutes to write a solution. Right? So I love doing this one because it shows that we're now what, in week 3 of a Computer Science 1 course. This is a fundamental thing. It takes in basic operations. How do you tell if something is divisible by 3 or divisible by 5? It takes in basic I/O. How do you print something, and how do you print something else? It takes in conditionals. If it's this one thing, print fizz, or if it's this other thing, print buzz. If it's this other thing, print something else. And finally, the thing that we're covering right now, it takes a loop because you have to do numbers 1 to 100. Okay? All right, so let's do this together. Right? Let's pass that that programming test to get that second interview. Right? Actually, now I take that back. Google was not the worst. The worst one was another one where I was given a 3-hour test on, and we had to use Blue Books, and then I got an on-site interview for 1 day, and that was actually easier than the Blue Book test. So. But that was a whole day, and there was like a math test, there was a quick math test, there was a coding test. It was terrible. Hopefully the job market for developers is a lot better nowadays, and they've got better filters than that kind of stuff. But at least they flew me out to California, or they flew me out to Wisconsin, wherever it was. All right, so let's go ahead and write the basic FizzBuzz program here. In fact, I'm going to copy this over to, no, we'll do it here. Right? All right, so help me out. First line. All right, we're probably going to want a loop, right? Do we want a for loop or do we want a while loop? For. Why do you want a for loop? You know exactly how many iterations you're going to go for. 100. Right? 1 up to 100. So let's go ahead and create an iterator variable here. Where should I start it at 0? Yeah, we should start at where now? 1, because you want to print numbers 1 to 100. I is less than 100? Less than or equal to. And in fact, if you want to do, you could go ahead and put that into a variable, right? So that if they said, okay, well, how would you do it if you wanted to do up to 1,000 instead? Oh, okay, I'll just change that one variable there, all right? Or they might use that as an opportunity to critique and say, oh, you shouldn't have hard-coded values like that. You should put everything into variables, right? So less than or equal to n. I plus plus. Yeah, go ahead.
The reason you don't put spaces in between the sides inside of your groups or
It's just my thing. I mean, if you want to, what would A style do? A style demo. I don't think A style is going to care. Yeah. But if we go C code beautifier, I'm sure that like the GNU standard would put a bunch of spaces in there. No, I don't want that one. I want that one. There we go. Format that. Google would put in a bunch of spaces. Mozilla, what would they do? They would put in a bunch of spaces, so maybe it's just me. GNU, they would put in a bunch of spaces too. They'd put in way too many spaces. LLVM, okay, everybody's putting in a lot of spaces, right? I don't know, it's a little bit more compact to me, I guess. Just be consistent, right? We're not going to grade you based on, are you doing it the way that Google would do it, or Mozilla would do it, or WebKit would do it, right? We're only grading based on consistency. All right, so let's go ahead and print out the number first. And I'll just print out %d and the line I. Right? Now, if I were to do this, of course, right, then I'm printing out the numbers 1 up to 100, which is basically what you're going to do in your lab next week. In your lab next week, you're going to do what's called coding kata. If you've ever heard that term before, it's borrowed from martial arts. Martial arts, you do the same exercise over and over and over again to develop muscle memory. I don't do martial arts. This is just a term that people have stolen from martial arts. And the same idea is here, that in coding, that you do the same code over, write a loop to do this, write a loop to do this, write a loop to do this, until that muscle memory, your mind muscle memory, knows how to write a loop like instantly. Right? You just practice until it's ingrained in you. Right? All right. So if I were to do that, I would just have the numbers. What should I do to make it not do that? Okay. If it's divisible by 3, we'll print fizz instead. All right. So if I is divisible by 3, then I will say printf fizz instead. Okay. Now, how do I say is divisible by 3 here? That's not real code. Modulus. I mod 3, and if the remainder of that is 0, then it's divisible by 3. Okay. All right. Else if I divides by 5, what were we supposed to print there? Buzz. All right. Okay. Else, and then print the number. Yeah, we've got more here. Let's make sure that this works though, of course, first. So let's jump all the way to the top here. What would we expect here? 1, 2, 3 fizz, 4, 5, 5 should be buzz. 6 is fizz again because 6 is divisible by 3, etc., etc. But when I get up to 15, 15 is divisible by 3 and 5. So what should I have done? Yep. So another check here. Else if I is divisible by 3 and I is divisible by 5, then, 0. There we go. Then go ahead and print fizzbuzz instead. Let me get rid of this I don't want to lose this, but fine. Printf fizzbuzz, end the line. Right. So is there a way to improve this code?
By putting it at the front of the
Oh, okay. Hold on to that thought first. But is there a way to improve just this code right here? Yeah.
Can't you just say if I is divisible by 15?
Yeah, if it's divisible by 3 and 5, mathematically that means divisible by 15. There we go. That's an improvement. Else, don't lose the original there. And put it there. Okay, there. So GCC, let's clear this out, and let's run this again and see if it works. 3, 4, 5, buzz, fizz, blah, blah, blah. That still doesn't work. Remember, what's fundamental about these if-else-if statements? They're mutually exclusive. The first one that evaluates to true is the one that gets executed. So when we get down to 15 here, it's divisible by 3, right? So it'll print out fizz instead of fizz buzz. What do we need to do? We need to promote this up to be our first condition, right? Because that's the most specific. If it's divisible by 15, then do that. Else if it's by 3, there, else, there we go. Right? Now the most specific condition here is going to be fizz buzz. Then this is a little bit more general because not everything is divisible by both. But some things are divisible by 3, some things are divisible by 5. And by the way, they're primes, so we don't have to worry about any of that stuff, stepping on each other's toes. And then what about this last one here? That's the catch-all. If it's neither this, neither that, then what do? We print the number. And I think we've solved it here. Let's find out. I see some fizz buzzes there. Fizz buzz. Right. What else should I check? 45? Where should 45 be? Fizz buzz as well. Right. All good. Any questions on that? All right, I think we're good. And if you want to go down the rabbit hole of fizz buzz, there's also enterprise level fizz buzz, which is a joke. So they took the basic fizz buzz and then tried to add as much nonsense to it as possible and make the project and the code as big as possible. And like enterprise software makes a special high-grade class of software that makes careful use of relevant software architecture and design principles. We call this over-engineering, right? And so they've done this intentionally here as a joke and as a demonstration of over-engineering things, right? Simple design is probably better design, right? Remember the KISS principle? Keep it simple. There's also, don't over-engineer things, or we'll talk about this later maybe. There's a Yagni, right? You ain't gonna need it, right? So there's always this tendency to, we might have this use case and that use case and that use case. We might want to write software to take care of all of these things. No, you just need to write software to take care of this one thing right now. All that other stuff is borrowing worry from the future. You ain't gonna need it, Yagni, right? So over design, pre-optimization, premature optimization. These are common themes in engineering and in coding, right? So there's another term of art there, right? But if you want to go down the rabbit hole and find out what other FizzBuzz stuff is out there, you can. Right? But it's a well-known problem, and that's why I still cover it, because it covers every single principle that we've covered for the first 3 weeks of this course, all in like 12 lines of code. Right? Okay. All right. Do we want to convert it to a while loop? Let's go ahead and just really quickly here convert it to a while loop. First of all, I would need to create the index variable there outside of the loop. Then I would have while I is less than or equal to n. Do I put a semicolon there? Nope, no semicolon. That's another difference there. Will this run? As is? 1, 1, 1, 1, 1, 1, 1, 1, 1. Remember, if you have the initialization condition, the continuation condition, and the increment. In this case, I want the behavior to be down here at the end of the loop, I++. And I'll get FizzBuzz solved again. Right? There's so many simple things that can go wrong with this, then it's probably, overall, it's probably nerves. People who are qualified for the job, they're like just way too nervous. They're bad test takers, or they're bad interviewers or something, right? And then they just freeze like deer in the headlights. Okay? All right, but there are plenty of imposters out there too, right? So let's talk about getting a loan for a car, right? So if you've gotten a loan for a car before, you know how it works. Not everybody does, right? But here's basically how it works. All right, let me show you. Suppose that you take out a loan, say for $10,000 over a 5-year period at a 5% interest rate, right? So in other words, and you're making monthly payments. So over 5 years, you are making 60 payments because, as we all know, there are 12 months in a year, right? So 12 times 5, that's 60 payments. The amount of each payment is given by this formula right here. That's the rate, which is the monthly rate, times the principal, that's the amount that you borrowed, over 1 minus 1 plus rate raised to the n, where n is the number of payments that you make. Well, if you take all these numbers, 10,000, 5, and 5%, and you plug it into this formula up here, you come out with $188.71. There's actually a fractional value down there, but do you ever pay? Can you pay like a half a penny? No. So what we're going to end up doing is rounding it. Okay? All right. And then what happens is that you start making your monthly payments. And you have a loan amortization table that looks something like this. In that first month, you will end up paying $41.67 in interest, Why is that? Let's come over here to Wolfram Alpha and as our calculator. And remember that 5% is 0.05 divided by 12 times 10,000. Right? That's the amount that you pay in the first month towards the interest. Okay? $41.66.6. What are we going to do? We're going to round it, right? That's why over here in our notes here, that's why it became 67. We're not going to round the number to the whole number. We're going to round cents. Okay? So be careful there. Now, if you take the difference between $188.71 and $41.67, that's $147.04. That's the amount that you pay towards the principal. You now owe less. Now you only owe $9,852.96. You do this every month. As you pay this down, the interest is not based on the original $10,000, but it's based on the balance each month. You paid it down a little, so you pay less in interest that month. You paid it down even more. Now you pay less interest. Your principal payments go up. Otherwise, you would never pay it off, right? You'd be stuck with that loan for the rest of your life, even though probably the car would die after a couple of years there. Right? I did look. You can get some beaters for like $3,000, but nothing cheaper than that. I couldn't believe it, right? And they are beaters, right? They are like early 2000s. Yeah, there was a PT Cruiser available. If you can imagine that. There's no, I can't imagine that it actually runs anymore. But anyway, all right. So what we're going to do is we're going to write a program, a full program, to do this loan amortization table for us. We're going to read in the amount of the loan, the number of years that the loan has, and then finally the interest rate here. And then we're going to produce this table. Right? That's going to be a loop. We're going to go for the first month, then the second month, then the third month, then the fourth month, etc., until the loan gets paid. Okay? All right, we'll leave Wolfram Alpha up here to verify some calculations and stuff like that. But otherwise, this is already in the notes, so let me go ahead and get rid of it. Okay? Some more real estate there. We're probably not going to get done with this today, but at least we can start on the basic input. Do we want to prompt for input and say, please enter this? Okay, thank you. Please enter this. Okay, thank you. Or do we want to use command line arguments for this? Okay, so let's do command line arguments. If argc is not equal to the number of command line arguments that I'm expecting, then I'll print an error message. Error, enter, what do we need? Principal, rate, annual rate, and I'll put an underscore on that or something. I don't know. Annual rate and what else was it? Number of years. Number of years. There we go. That's good enough. Right. That's another engineering principle. What's better than good? Good enough, right? As long as it meets specs, you're done. Ship it. All right, because whoever approved the specs, it's their problem now. Right? All right, so how many should I actually expect if I'm expecting 3 numbers as input? 4 because of that A dot out, right? That first one. So if it's not equal to 4, then I'm going to exit on them. Otherwise, I know that they entered in a principal, an annual rate, and a number of years. So double principal, double annual rate. Oops, oh, I was in a Python mode there. Double years. Actually, should years be a double? No. Loans don't work like that. 5 years, 10 years. There's not 10.5 years. Maybe there is. I don't know. But we'll just say that it's not. Okay? So principal, annual rate, and number of years. That means that we need them read them in as command line arguments. What was that function that I used to convert from alphanumeric to floating point number because it's a double? A2F. Argv sub 1. Why 1? 0 is the executable file name. Right? All right. Do the same thing for the annual rate. A2F of argv sub 2, the second one, or technically the third one. And A to I. Why A to I? Because it's an integer, right, of argv sub 3. Okay? With only 5 minutes left, let's go ahead and just get this principal right here. The rate times the principal. Remember, that's a monthly rate, so let's have another variable. You're not paying by the variable. If you have another concept, make another variable. Monthly rate is equal to the annual rate. And how many months are there in a year? 12, right? Good. Right. Oh, sorry. Yeah. Divided by. Now, do I need to put a dot zero there? Technically, no, because the annual rate is already a double. So I don't have to worry about integer truncation here. Right? So double monthly payment is equal to the monthly rate times the principal, right? Divided by, and then what was the rest of it? 1 minus 1 plus rate raised to the n. So 1 minus 1 plus the monthly rate raised to the power negative n. Yeah, none of that is correct. Right? So help me out. Yeah, first of all, I need the numerator in parentheses. That's good. That's what it looks like now. 1 minus, oh, did I do plus? No, I did a minus there. How do I raise to a power? I can't use the caret there. Pow. Right? Pow of that raised to negative n. There. Okay. Verify that I am indeed bringing in the math library to help me here. All right. And now let's print out, let's just as a sanity check here. Oh, sorry.
N, shouldn't that be, we have
Oh,
not,
yeah, you're right. We have not defined n, so this is not going to compile. What was n before? 60. That's the number of payments. So month. So here, should I call it n, first of all? Years times 12. I mean, that's what it is in the formula, right? Formulas are written by math people. Math people don't like writing out words for their variables. That's why they have X, Y, A, B, C. They also don't know what those stand for because they're just thinking of things abstractly. But our variables do stand for something. What does this stand for? Months, right? That is a much better variable name there. Now let's just make sure that our calculations are correct. They're not, but we'll fix it next time. Monthly payment is going to be $sign because it is dollars. Percent %F and the line, and then monthly payment. GCC. Oops. What's wrong with you? Oh, there's a missing semicolon somewhere right there. There we go. I should have a return 0 at the end. I probably accidentally got rid of that somehow. GCC. All right, and then what do I need to do for to bring in the math library? -lm. There we go. All good. All right. I need to enter the principal. So I've got a test case, ready test case right here. 10,000, 5 years, 5%. So 10,000. What was it? Then what was the order? Annual rate is 5%. So 5%. It's on a scale of 0 to 1. And then 5 years. Ah, is that correct? Nope. So, that is 10,000, that is 5. Okay, there we go. Yep. What did we do wrong?
denominator in parentheses.
Yeah, okay, there's one thing that we did wrong. The denominator needs to be in parentheses. Good. Did that fix the problem? Almost. $188.71.2336. What do we want? $188.71. All right. So there is a round function. Let's try it. Monthly payment is equal to round of monthly payment. Let's see if that fixes it for us. All right. Can't spell. Monthly payment. Monthly payment. There we go. All right. Oops. There. $189. Is that correct? No. What does round do? It rounds to the nearest whole number. When we come back on Friday, we'll fix this. All right? We're not going to have to write too much code. Think about a trick that you could do with this so that you can get it to round to cents.